Okay, so in our second and last pre-lecture video for today, I'm going to introduce some of the background concepts we need to be thinking about when we are going to introduce this new topic called regularization. We'll focus on that on Monday's class, but here I'm going to kind of turn our attention back to the coefficients of the predictors that we learned and how we're going to use that to try to prevent overfitting. So we're going to kind of look back at coefficients and make sure we kind of understand what they're saying and kind of what we can interpret from them. So to start, we've already seen this kind of concept before of interpreting coefficients. I haven't shown you this picture exactly, but it's the same idea of something I've drawn earlier, which is when you're using linear regression with one feature, we sometimes will call this simple linear regression. It has one feature. It doesn't get much more simple than that. Then you have a coefficient for the intercept and a coefficient for the slope that you have to learn. And so we can interpret what that means. Like, if you see that if you learn the equation 2 plus 5x, you know that the intercept is going to be your estimate for W0, and the slope, the rise over run, is going to be your estimate for W1. So in this example of price houses, and you learn the coefficients 2 and 5, you would know that the price of a 0 square foot house is 2, and that if you increase the square footage of a house by 1, its price would increase by 5. So you can interpret in a result from the model that results from your training and make inferences about the world. So in the simple linear regression case, it's very straightforward to do, interpreting coefficients just like slope and intercept. It gets slightly more complicated when you want to think about multiple linear regression, where you're using multiple features with your model. In this case, when you're learning multiple features, then you're going to have coefficients W hat 0, W hat 1, and W hat 2. And in here, I'm referring to the first feature x1 being the square feet, and the second feature x2 being the number. Okay, so number of bathrooms and square footage, those are going to be the two features I'm using. And now things are very similar to what we had before, but just a tiny bit more detailed in what we can claim about our result. So if I was interested in interpreting what W2 or my estimate for W2 means, I have to specifically talk about it in terms of me holding x1, the other feature, constant. So when I'm talking about interpreting W2, I'm specifically thinking about only as x2 varies, holding x1 to be some fixed value. So maybe I'd pick like x1 is 100 square feet or some arbitrary number, and I would think about holding everything constant there, and kind of this three-dimensional setup where you have these two input dimensions and one output dimension. If you hold one of the inputs constant, that's like slicing a piece of paper through your learned predictor, which in this case is a plane, since there's 3 dimensions rather than a line where we had 2. And so here in this multi-dimensional case, we're kind of slicing down one dimension. And if you kind of treated that slice as like a piece of paper and looked at it, then the way that plane intersects with that slice is a line. And we can interpret this just like we did before. That when you're now considering how W2 changes the price for each unit increase in x2, which in this case is number of bathrooms. But this is only accounting for when x1 is fixed. It's not going to make statements about what happens when you vary both, only about when you vary one of them. So it's the rate of change holding everything else fixed. That might sound a little bit pedantic, but it's a very important thing to think about when you're trying to interpret these coefficients, that they're kind of limited in what they tell you. It's just how the feature changes the output, assuming everything else is fixed. This works more generally past just 2 dimensions or 3 dimensions. If you have D features and your intercept, you could do the same thing. Each coefficient tells you how one feature changes the output, holding everything else fixed. And this works very well even with large dimensionality. There are some general cases where this interpretation doesn't quite work, particularly when the features are all related to one another. So a great example is if you're doing polynomial regression and all your features are polynomial expansions of your input, like x x squared, x cubed, etc. It's not really possible to consider, let's fix x and x cubed, but let x squared vary. That doesn't quite make sense because they're all based on this underlying thing called x. So in that case, when you have all these related features, it's much more complicated to interpret what the coefficients mean. They don't give you the same intuitive understanding of how the underlying process works. You can't really fix those other features, so then this interpretation of coefficients kind of goes out the door. This works quite well when you have a bunch of relatively separate features that aren't coming from the exact same data input. So that's just one thing to keep in mind, that this does only work if you're able to fix the other features. Sorry, I think my voice cut out right there. Let's actually make sure that's not cutting out. Okay, that should be better if that was cutting. Okay. So interpreting coefficients is great. I want to talk a little bit about what I bringing up interpreting coefficients. So namely, when we think about having some data set we're trying to fit a curve to, and suppose I'm using a really high degree polynomial, one that's like bounces up and down quite a bit. It turns out something very special happens to the coefficients. It turns out in this case, when you have this polynomial bouncing up and down quite a lot, it turns out that for all of your learned coefficients, or at least many of your learned coefficients, so W0, W1, W2, all the way up to W hat D, it turns out that the magnitude of all of these coefficients, or at least many of the coefficients, tends to be quite large, much larger than 0. So empirically, one way of spotting these polynomials that are bouncing up and down, if you can't quite visualize them, is looking for really large coefficients, potentially meaning that they don't quite, that there might be a lot of bouncing up and down here. That might be a sign of overfitting. So when you have this bouncing up and down behavior, it tends to be that the coefficients are large. And the idea there is that maybe we can use this idea of coefficients being too large to prevent overfitting. We can control the magnitude of the coefficients. We could potentially prevent ourselves from learning a model that bounces up and down like this, that might be overfit. So that's what we'll be talking about in class on Monday. There's a few other things I want to talk about in this video. So first, I actually want to show you a code demo I wrote that actually lets you experience this phenomena of the coefficients growing as you overfit. So I'm going to have this linked on EdStem. So you can run the notebook in EdStem, but I'll also link to this other tool called Collaboratory, which is like a Google Doc version of a Jupyter Notebook. Same idea of Jupyter Notebooks in EdStem. It just looks a little different. It's the same fundamental idea. The reason is one of my demos, or a couple of my demos for today, have interactivity. So they actually have visualizations you can interact with, and EdStem doesn't render those quite well. So I'll have it available on EdStem, but I'll also link to Colab if you're interested in checking out and playing with the interactive thing. A lot of the code, like before, in most of our demos, I'm trying to show off a cool thing or an interactive thing. Most of the code is probably going to be a lot more complex than anything you're going to have to write. So don't worry too much about the code here, but I'll walk through what's going on. We're defining some functions, so we're defining the true function f here. So this is one that we don't technically know. We're not supposed to know what f is, but I'm just defining some f to visualize. And then I draw some data from this function. So I generate some random x's, and then I generate a bunch of y's that follow this function f. And then I just plot out that data, showing that my data set is approximately close to this true function f, but not exactly there. Okay, let's talk a little bit about overfitting in this first demo. So the first thing I want to show is that, something that shouldn't be too surprising given our discussion on Wednesday, is that if you use a degree polynomial that's too large, it will overfit. And so here I have some interactive code that has a slider that you can increase the slider and change the degree polynomial you're trying to train. So right now I'm training a degree 0, which is why we learn a constant line. If I up it to degree 1, we learn a line. If I up it to degree 3, we learn this kind of cubic curve. You can go up to line 8 or degree 8, and it starts wiggling around more, and you can keep going, and it keeps wiggling and wiggling more and more. As you give it higher and higher degrees, it has more degrees of freedom, and there it's able to bounce up and down quite a lot. And so my claim is that when you have functions like this that bounce up and down all the time, that the coefficients that you're learning are quite large. And that's what my second demo is showing. My second demo is going to show, well, let's look at the magnitude of the coefficients as the degree of the polynomial grows in this case. So actually looking at the coefficients you learned and taking their average size. And you can see that the coefficients for small degree are things like less than 10 squared. 10 squared is 100. They're all like relatively small. When it's small degree, they're actually quite small. Now you're like, wait, 10 things being near 10 squared doesn't sound that big, but look at the scale that these blow up as you increase the degree. When you're at degree 30, the line's all the way up here, and that's 10 to the 14. That is a huge number for a coefficient, right? 10 to the 14 is a gigantic number to claim as your slope. And so you see this blow up in coefficient size as you increase degree. And so generally, when you see these super, super, super large coefficients, that might be an indication that you're overfitting. So this is like just empirical evidence that this does happen, that you don't just have to believe me. One thing I'm going to mention that we're going to find useful in our discussion is sometimes it's annoying to talk about all these individual coefficients separately. So every once in a while, we'll also talk about this idea of the coefficient vector. All of the coefficients you learn in one big array. And so that's sometimes nice just talk about this one thing, this one array with all your coefficients. We don't have to write out W0, W1, W2, all the way to WE every single time. Okay? So I just wanted to mention that we are going to use this notation of just W hat to refer to the vector of all your learned coefficients. Okay, so we talked about the coefficients growing, but one thing that you pay attention to is that overfitting is not necessarily limited to polynomial regression of large degree. It could also happen anytime you use a large number of features. So anytime you're using a model that's complex. And why? Well, overfitting tends to happen when you have overfitting is relative to how much data you have. If your model is too complex for how much data you have, you're going to tend to overfit. And it turns out with more and more features, or more and more complex features, you can get higher and higher complexity models. So this is kind of going back to what I said earlier in this. One of the things I want to discuss is that complexity is relative to how much data you have. So like if I have this much data, a degree 14 polynomial is definitely going to overfit this much data. But if I had another polynomial trained, another model trained, another model trained on a lot more data, this curve it learns is much smoother. It's much harder for something to overfit when there's lots of data to train from. And this was something we talked about on Wednesday, showing that the more data you had, the harder it was to overfit. And one way to spot this is this idea that in this kind of case with these wild curves, we have large WJs. But in here, when you train the same degree polynomial, but with a lot more data, you have moderate WJs. Or reasonable WJs. And here I also have a demo that if you're curious, you want to play with. Here is the ability to look at different degree polynomials, or one degree polynomial with different amounts of data. These are actually just the graphs I generated on that slide. You can actually check this out. Try different amounts of data set sizes. You'll find that the same degree polynomial tends to not overfit with lots and lots of data. And this kind of gets at this idea that the complexity of your model is not just degree polynomials, but how many features you have. So the number of features you have control your model complexity. So how do the number of features affect overfitting? Well, if you only have one feature, To avoid overfitting, you need a representative sample of all XY pairs, where X is your input feature and Y is your output. And that is a possible task to do. It's hard, but we can do this quite frequently. We can download data. We can download enough data that, I only have 14 or 13 data points here. And so a degree 14 polynomial is quite high degree. But you can imagine downloading data that has thousands or 10,000 rows, and you can get a nice, hopefully representative sample of the space. So this is difficult, but not unachievable. But once you start including other features, things get much, much harder. So if you use D features, you need to make sure that your training data is representative of all combinations of X1, X2, X3, all the way to X. So if you have D features, you need to make sure you have a lot of representative data to avoid overfitting, because you need to make sure you see all combinations of these features. And so it is much, much harder to get representative data for many features. Even for a moderate number of features, like 5 or 10, getting something like 100 or 1,000 rows might not be enough to cover the whole space. As you increase the dimensionality, you really need lots more data. Make sure you get this representative. And this is a quick introduction to something we'll see later in the course called the curse of dimensionality. That generally more data in terms of more dimensions isn't always better, because things get much trickier to work with when you need all of these combinations of different features to get a representative sample. So we're going to run into this a few times this quarter. So what I'm going to leave us with is a thought experiment that we'll pick up with on class on Monday. So last time we introduced this procedure of using cross-validation or a validation set to choose the right degree polynomial P, because we saw that some degree polynomial P might overfit if we don't have enough data. And this process works fine. We're wondering, is there a way we might change our model around a little bit, change something in our ML pipeline to try to prevent overfitting in the first place? So is there something we can do to make it so that our model just doesn't overfit to start with? So then we don't necessarily need to do this entire train a bunch of different models on different validation sets that we had to do before. So the question is, can I actually achieve this in the model itself? Can I change something in my ML pipeline to prevent overfitting? And in the case of polynomial regression, it might not be obvious why we need this different approach, because we can just control the degree P for the complexity. But there's lots and lots of other models that aren't just degrees of polynomials. And so we're going to introduce an idea that's more general. If, for example, you want to just choose which subset of the features you want, there's actually so many possibility subsets of features. There's actually an exponential number of them that it's going to take way too long to try all possible complexities. So if you have D data inputs, there are 2 to the D possible subsets of them. Things that are exponential like this grow very quickly. Like just graph out 2 to the X, and just look even for a moderate number of inputs, like 50 to the 50 is the gigantic number of possible models you'll have to try. So we're going to see if there's a way that make models that just avoid overfitting in the first place. And the big idea for what we're going to introduce in class is this idea of making models that regulate themselves. What I mean by that is a model that is aware of what happens when it overfits, namely the coefficients get large. And so is there a way to bake into the model or bake into the ML pipeline a mechanism to stop overfitting? In some sense, try to prevent large coefficients in the first place. And we'll call this idea of trying to control the learned coefficients regularization. And this is going to be a very important technique that we'll use to prevent overfitting. We'll explore this in Monday's class and Wednesday's class. We'll talk about what regularization is and different ways of trying. But this is just background information for where we'll pick up, talk about this